Okay, I will present my efficient solution. It only consists of tabular data, so it's actually simple, efficient, and it don't have any complex architecture. So it's more about conclusion and findings. And my steps are conventional machine learning steps, actually. About my background, I graduated uh, as a computer scientist. I have been working as a data scientist for 3 years. I'm also a Kaggle competition master. In summary, I used large EBM framework. It's highly customizable and it's very fast and lightweight. Random undersampling method, one of the crucial steps in medical tasks, and age, lesion size, and features derived from them. These features were mostly effective. For hyperparameter tuning, I used Optima framework. It has very good algorithms for hyperparameter search, like TPA-3 search and Gaussian process. And it takes only 3 minutes to train the model. For feature engineering, we have features related to lesion size and color. What set my work apart from others was implementing patient-based partitioning. I generated anomaly score like features by normalizing the features within each patient. According to my hypothesis, a patient's characteristics such as height, age, skin color, and gender can affect the expected lesion size and color. So I normalized them as a new features. I experimented with LAB color space. I tried to transform it to RGB color space and HSL color space, which didn't improve the score. I also tried to utilize RDX features. I tried to weight the samples based on their RDX features. It didn't work well. Uh, the patient's lesion size and interactions with age were the most influential features. By the way, there are some features named as one hot. They are categoric features. I encoded all the categoric features. So sorry for the column names. I think 145 is the one of the lesion locations. And there are many age-related features because some patients have more than one age. That means that creates a time series like situation. Uh, so some of the most influential features about age. On the right-hand side, you can see most effective two features, age approximation and clean size. They are not in the top side, but you can see in the plot they are very correlated with malignant cases. And other aspect of feature importance, I derived it from large GBM framework. You can see there are age-related features, also some features that end with norm word, that means normalized over patient. Hyperparameter search, I used Optuna, as I said. You can see that it works very well. It increases the partial area under curve over iterations with selecting best feature combinations. And most important hyperparameters are those associated with regularization. So we can say that overfitting is one of the major problems in this data set because we can see most important hyperparameters are about regularization, like L1 regularization or minimum data in gradient boosting, tree leaves, etc. Important and interesting findings. One of the most impactful observations, according to my observations, the majority of the errors made by the model are false negative. I investigated the common characteristics of these samples, and as a result, I found that most of them involve lesions with a diameter of between 2.5 to 2.75 millimeter. As you can see from the figure, lesions smaller than 2.5 millimeter in diameter are mostly malignant and easy to classify. However, notice that non-malignant lesions peak at 2.5 millimeter. This narrow region is dominated by non-malignant lesions that are very similar in shape to malignant lesions. Therefore, it becomes difficult for the model to detect these malignant lesions. And in the right figure, you can see that our model Shapley values are negative in that narrow region. Our model estimates usually non-malignant case for this narrow region. I also conducted a study on data quality. I examined how the data was distributed in different validation folds and how their correlation with target changed. The lack of positive labels causes some deviation in the distributions. You can see in the graphs, distribution of features changed over folds. And also distribution of modal probabilities are changed over folds. We can also conduct these experiments on real test data to see why maybe we can find the way why our scores are lower in private data set. And you can see that correlation of features change over folds because of low positive cases. And I also performed segment analysis. One hot one means gender in the y-axis, zero means male, and one means female. You can see how model performance changes over different age segments and different genders. Overall, actually, it's a little bit harder to predict malignant cases in female patients. Its score a little bit lower compared to male patients. But in some age segments, especially the elderly patients, the score is lower both for female and male patients. And you can see the performance of model over different age segments and diameter of lesions. Mostly elderly patients have lower scores. Also, the diameter of lesions higher and lower end, they affect model scores. In the lower end, we know that from 2.5 to 2.75 millimeter, zero non-malignant cases are dominated, so it's hard to estimate. On the other hand, for big lesions with higher diameter, it's also hard to estimate. We can conclude that. Training method, as I said, I used large GBM. I didn't create any complex architecture because it may overfit to training data. I just used used one hyperparameter set. All these 5 models use same hyperparameters. I also created a pipeline that first data is undersampled, 0 cases. I eliminated some 0 cases. If I remember correctly, 0 to 5, negative to positive ratio is 100 at the end from 1000. That means every one of 10 negative classes, negative samples are eliminated. At the end, I used different seeds and I assembled 5 different models and averaged them. I also tried feature selection to see if I can achieve same score with less feature count. And I found that similar scores can be achieved using only half of the features. However, my most successful model were using all the features.